Hi everyone, welcome to CS 188 Section 3, and today we'll be talking about CSPs and games. Okay, so I went over CSPs last time, but I'll set it up again and we'll go into actually how to solve CSPs. So let's consider our usual example, which is coloring Australia. So if we have Australia, and I divide it into states, and let's see, so I'm going to call this state 1, state 2, state 3, state 4, and state 5. Then to define a CSP, you need three things. So first, we're going to have our variables. So we're going to have our variables are going to be x1 all the way to x5. Next, we need domain. So what values can our variables take on? So in this problem, we're going to assume they all have the same domain, and they're the three colors R, G, and B for red, green, and blue. And finally, we have a set of constraints. So for this, we're going to say that no adjacent states can have the same color. So xi does not equal xj if neighbors. Okay, so the goal of the CSP is that given our initial state, which will be all of our variables, x1 through x5, not having any values, we want to find values in the domain, so red, green, or blue, to assign to all of them, such that they satisfy all of the constraints. So once we assign colors to all of the states, and none of the adjacent states have the same color, then we're done. So that's our goal test. So when solving these, the main approach, which we'll improve upon, is called backtracking. So backtracking is like our normal search that we've done before, like DFS, BFS, of those sort. But we have two additions that are specialized to CSPs. So the first one is we consider one variable at a time. So one xi at a time. So we can choose this ordering however we want. So we can do x1, then x2, then x3, or x5, then x4, then x3. So we have the freedom to choose the ordering. We'll talk later about that there are smart ways to choose the ordering that help get the solution faster. But in general, you can choose any order. Then the second thing that backtracking does is that it checks the constraints as we go. So we check constraints as we go. So what I mean by this is that if we set, let's say we do x1 equals r, and then next the algorithm decides to do x2 equals r, so this violates a constraint, so this is bad. So normal search would just keep going. It would keep assigning x3, and then once they were all assigned, it would say, uh-oh, bad. And then it would go back. But when we're doing backtracking search, it'll stop here, right as we assign x2, and it violates the constraint. So in this way, we don't have to go as far before we realize we made a mistake. Okay. So now that we have defined backtracking search, we're going to talk about various improvements. So the three of them are filtering, ordering, and structure. I'll spend most of my time talking about filtering, which is, I would say, the most important one, and then briefly go over ordering and structure. Okay, so filtering. So the idea of filtering is to cross off bad options. Now, what do I mean by bad options? Well, like I said before, if I assign state 1 to be red, a bad option for state 2 would also be red. So that's going to be how filtering is going to work. So when we talk about filtering, we're going to talk about arc consistency. So first, let's define that. So let's say we have a state x, and it points to a state y. So we say this is consistent if and only if for all values that x can take on, that there exists a value for y that doesn't violate the constraints. Okay, so this can seem fairly abstract. So let's do a concrete example of enforcing arc consistency. So in general, this is arc consistency if this is true. But what we'll be doing is we'll be enforcing arc consistency. So we're going to be comparing for all x, for a given x and a given y. Does this hold for all values in the tail? So we're going to be looking at x. And if there's a value that violates this, we cross it off. Okay, so let's do an example. It'll make more sense then. So let's say that we color state 3 green. And then I'm keeping track of all my states, x1, x2, x3, x4, and x5. And for each of them, I'm keeping track of their domains. So when it's written, that's a valid value. If it's crossed off, that means it's not allowed. So initially, I start off with all of them allowed. And then I arbitrarily just chose x3 to be green. So I cross out the other colors. And now I want to enforce arc consistency to 3. So what does this mean? I'm going to add every arc that points to 3. So I'm going to add 1 to 3 because they're neighbors. So if I draw the graph of what this would look like, it would look something like this. 1 and 2 are connected. That means they have a constraint between them. 1 and 3, 2 and 3, 4 and 2, 4 and 5, and 3 and 5. So now that I'm considering 3, I add all arcs that point to it. So 1 to 3, 2 to 3, and 5 to 3. So now what I want to do is I want to check and ensure that all of these enforce arc consistency. So I look here and I look at 1 and I say, for all values that 1 can take on, is there a valid value in 3? So I go one by one. So for R, is there a valid value for x3? Yeah, green. That satisfies constraints. Okay, cool. Now I go out for 1, for green, is there a valid value for x3? The only value you can take is green, and green can't be next to green. So that's not okay. So to enforce arc consistency, I need to make sure that I cross that off. Now continuing to blue, this will be just like red, and it'll also be valid. So now I've enforced arc consistency for 1 to 3. So now I'm done. So I've done that. Now I would do the same thing for 2 to 3 and 5 to 3, and if you run through the same process, they're exactly the same as 1. So I would also cross off green and be good, and I would also do that for 5. And that would also be good. So that's how to enforce arc consistency, and in general, this is called forward checking. So forward checking is, first, you would assign a variable, say, to a domain value, D. And then you add all arcs that point to it. And then finally, you enforce arc consistency on those arcs. Okay, great. So that's forward checking, and that's enforcing arc consistency. Now, there's something else though. So we can do forward checking, which only checks for the value that we assigned. But since we're crossing off values in other domains, like in this example, we crossed off values in x1, x2, and x5, this could propagate to other variables, that there could be other variables that would also have their domains, that other variables that would not be arc consistent anymore because we were changing the domains. So this brings us to enforcing in full arc consistency. So let's go over that. Okay, so now we're going to do arc consistency. Before we just did forward checking, which was just for all arcs pointing to the assigned variable, but now we're going to get more general and enforce that all arcs after the assignment are consistent. So let me write out some pseudocode for enforcing arc consistency, and then we can compare to see how it's different from forward checking. Okay, so we have arc consistency. Okay, so we'll assume we just assigned a variable. So we just assigned a value to xi. So just like before in forward checking, we add all arcs to the queue that point to xi. Then for each arc, if that arc violates arc consistency, then we cross off those values of the domain. And then this is where arc consistency differs from forward checking. We add all arcs that point to this tail. Okay, so let's show the difference between forward checking and arc consistency. So again, if I do x1, x2, x3, x4, x5, I have all the values, RGB. And again, I choose x3 to be green, so I cross off the other values. So, like before, I add all arcs that point to it. 1 to 3, 2 to 3, and 5 to 3. And again, for the first one, I enforce consistency, so I would cross off green. But now if I'm doing arc consistency, I add all arcs that point to 1. So I cross it off, and in forward checking, I would just go to the next one, but now I have to add arcs to my queue. So everything that points to 1, so I would add 2 to 1, and I would add 3 to 1. Then I would continue and I'd look at 2 to 3. So I would do 2 to 3, and I would also cross off green. And now I have to add all arcs that point to 2. So then I would add 1 to 2, 3 to 2, and 4 to 2. And I continue this process. So the key thing is that this is the difference between arc consistency and forward checking. So as you can see, arc consistency will take more time since you keep on adding arcs, but it also prunes the domains much more. So we're going to cross off more values. Okay, so that's it for filtering. Now let's talk briefly about the other two, ordering and structure. So for ordering, what we're considering is two questions. Which variable should I choose? What order? And then the other one deals with the other part of CSP, which is the domain. So what value in the domain should you choose, given a specific variable? So we have two heuristic approaches which work well to help speed up solving the CSP. And for dealing with the variables, we have something called the minimum remaining value. And this is MRV, is the acronym. And then for dealing with which value in the domain should you choose, we have least constraining value, which is LCV. Okay, so there's two intuitions for each of these, and they're similar but different. Okay, so for one, minimum remaining value is you choose the variable with the least number of values left. So choose xi with the smallest domain. So if I have two states, x1 and x2, and RGB and RGB, and x2 has two values crossed off, and I have to choose, okay, do I want to assign a value to x1 or do I want to assign a value for x2? I would choose x2 because it has the smallest domain. Now, why would we want to do that? So this has the idea of failing fast. So we noticed that when solving the CSP, we have to assign a value to all the variables xi, no matter what. So if I have to assign a variable to x2, I might as well do it sooner rather than later, because it has the smallest domain. So assume, let's say we had a situation in which we did x2 last and x1 was neighbors. So I could have tried out many things. I could have, let's say I chose green, and then I go on and solve, assign to x3 and x4, and I keep going. And finally, I come back and I'm like, okay, now I'll assign x2. But that's not valid because x1 and x2 are neighbors. And I found this out way too late. So the idea of minimum remaining value is to choose the most constricting of the constraints first. Okay, now for 2, it's kind of the flip side. So what value in D should I choose? So we have to assign all variables x1 through xn to some value, but we don't actually care which value, just whichever one satisfies the constraints. So we want to choose the one that violates the least number of constraints. Now, how would you choose this value? So one option is that, let's say we have x1 and we have r, g, and b. You could take, let's say, in your head, assign x1 to r and enforce arc consistency. And you could do that for r, and then you're going to count number of domains crossed out. So that's a sense of how much violation did this assignment cause. And then you could also do this for green in your head and also for blue. And then you would compare all of them and take the one that violated the least. So let's say R violated 2 constraints, green violated 4, and blue violated 3. Then I would choose to assign x1 R. Okay. Finally, we have structure. So in structure, the big question is, can we exploit the graph structure? So let's say we have the CSP that looks something like this. So this is something similar you should have seen in lecture. And from lecture, you were told and hopefully know that if you have a CSP that's a tree, you can define an ordering on it. For example, if it's something linear, and then we can solve these really fast. So what we want is to make a tree. So if we have this graph up here, to make this a tree, the simplest way would be to somehow remove 5. So we can't remove it, but we can assign it a value. So I can say, okay, 5, you're going to be red. And then the rest of the graph becomes a tree. But perhaps this won't work out. So if that doesn't work out, then I try green. Now it's a tree, and now I can solve it. And if that doesn't work out, then I can try blue and solve the rest. So for structure, the main tool will be, can we assign certain nodes to fixed values, such as 5 right here, such that the rest of the CSP is a tree. Okay, so that's it for CSPs. So now we'll talk about games. And in particular, we're going to talk about adversarial games. So before we were considering games in which there's only one player. So it went Pac-Man, and then Pac-Man would go again, and then Pac-Man would go again, on and on and on. And the goal was, for example, to eat all of the pellets. But now we have an adversary. So it's going to go Pac-Man, and then it goes the adversary, the ghost. Then it goes Pac-Man, and then it goes the ghost, and on and on and on. So now what we're going to consider is we're going to consider zero-sum games. So what this means is that something good for Pac-Man is bad for the ghost, and something bad for Pac-Man is always good for the ghost. So they're basically playing tug of war. So now we're going to have these search trees, but they're going to be game trees. And each level is going to alternate between the players. So we're going to have, at the top layer, we'll consider Pac-Man. And Pac-Man is going to want to maximize the score. And then, let's say Pac-Man has 3 options, which correspond to different moves. So for example, Pac-Man can go left, down, or right, and then it becomes the ghost's turn. And the ghost wants to minimize the score. And then let's say that the game ends after that, and there's some terminal values that the game can take on. So the game could go on longer, or these could actually be the scores from searching longer, but let's just say that these are the scores. Okay, so now what we're going to do is we're going to do Minimax, which is solving for the optimal move that Pac-Man should do, given that the ghost is also playing optimally, as in their best interest. So we start here at the very top and we go left, and now we're at the minimized layer. So the ghost will choose the minimum of all the values that it can obtain. So 3. Okay, so that's what left will get. Now if Pac-Man goes down, we get to the ghost and it can do 2, 4, or 6. The ghost chooses the minimum 2. And now Pac-Man considers going right, and the ghost has 3 options, 14, 5, and 2. And the ghost will choose the minimum 2. So now Pac-Man has 3 options. It can get a value of 3, 2, or 2. So Pac-Man will choose the maximum score of 3. So that's how you do Minimax. But now we noticed that we looked at some nodes and we did some extra work that we didn't really have to. So let's look at what we did. So we started at the root, we went to the left, and we got 3, 12, and 8, and the ghost chose 3. Okay, Now we go to the center node and we look at this first one right here. So we look at 2 and we assign 2. Now we notice something interesting. Will Pac-Man ever choose to go down? So the ghost can force a 2, but if Pac-Man goes left, Pac-Man knows he can get a 3. So it doesn't really make sense that we have to keep looking at the 4 and then at the 6. We know Pac-Man won't choose to go down. We know Pac-Man would rather go left. So now this brings us to alpha beta pruning. So the improvement to Minimax is to add alpha beta pruning. So as we're doing Minimax, and we're going to add 2 variables that we keep track of. So we're going to add alpha and we're going to add beta. So what is alpha? It's going to be Max's best option on the path to root. So the root of the search tree. And beta is the exact opposite. It's Min's best option on the path to the root. Okay, so now let's solve this by using alpha beta pruning. So let me erase these values and we're going to resolve it and see if we can more efficiently solve it. By more efficient, that means expanding less nodes. So when you do alpha beta pruning, you always initialize pessimistically. So what's the best value that the max can get? We're going to be pessimistic. We're going to say minus infinity. Now, what's the best value that min can get? We're going to be pessimistic. Now, beta wants to minimize. So what's pessimistic is going to be plus infinity. Sorry. Okay. So now we go search to the left and we pass down the values of alpha and beta. So alpha is minus infinity and beta is plus infinity. Now we're at the min layer. So you only update alpha if you're at the max layer and you only update beta if you're at the min layer. So we're at the min layer and beta is the min's best option. So we look at 3. So what's better, 3 or plus infinity? Well, clearly 3. So beta becomes 3. Now we look at 12. What's better, 3 or 12? Well, 3 is better, so we keep it. What's better, 8 or 3? Well, 3 is better. Okay, so the value of this node is 3, and this is the value of alpha and beta. Now we pass the value 3 back up, and since we're at a max layer, we update alpha. So what's better, 3 or minus infinity? Well, we want to maximize because we're at the max layer. So we update this to be 3. Okay, so now we go down and we pass down our current values for alpha, which equals 3, and beta, which equals plus infinity. So now we look at the first one, and it's 2. So what's better, 2 or plus infinity? Well, we want to minimize, so 2 is better, so we cross it off, and we get 2. So now we've reached the crossing point. So for alpha beta, we know when to prune, or when to stop searching the other nodes. When we're at a min layer, it's going to be when beta is less than or equal to alpha. So this is encoding the intuition that we had before. So if beta can do better, can do better than alpha, which is the max's best option, then alpha, which is max, would never go here. So now we're done. So we're not going to look at the other ones. And the value here is 2. So we pass the 2 back up. And 2, so what's better for alpha? Is it 2 or 3? Well, 3 is better, so we leave it. And now we pass these values down to the right. So we get alpha equals 3, beta equals plus infinity. Okay, so what's better for beta? 14 or plus infinity? We get 14 is better. What's better for beta? 5 or 14? Well, 5 is better. And now what's better for beta? 2 or 5? Well, 2 is better. And there's no more nodes to look at, so we didn't actually get any help here. Now we take the 2 and we pass it back up. Is 2 better than 3? Well, we're alpha, so we need to maximize, but 3 is better. So now we're done. So this value will still be 3, but look, we saved by not expanding 2 nodes. So that's how alpha beta pruning works. And in general, this is only depth 2, but it can go much farther, and you can apply the same algorithm, alpha beta pruning, recursively.